now we can start the question round. I think still nobody of the fifth presentation has shown up. So we can start with a question for this presentation, please.
All right, so I've got two questions.
Okay.
Okay.
Even the third one would be allowed.
Okay, so the one, you mentioned that those even grade Dewey keys.
Even grade elements.
These even grade elements represent a rigid body transform.
That's correct, yes.
So say you wanted to do something like, not stop motion planning for a physical machine, but maybe computer graphics or something like that. You need some other kind of affine transformation that's not necessarily rigid body. Like, could you do scaling, and would that be like an odd grade element?
Yes, you can do those sort of things. There is a whole host of transforms that are available within the language of geometric algebra. We've chosen rigid body motions because that's what we're so interested in. But within the conformal geometric algebra, you have many, you have lots of conformal maps indeed. So yes, it's not at all restricted. You just have to expand your algebra slightly. There is capability.
And then I think purely in terms of rotation, how would, because you compared a lot these conformal algebras to matrix multiplication, or matrix rotation matrices and so on.
Yeah.
But how would it compare for rotation to something like a quaternion?
It is quaternion.
It is a quaternion.
Well, that's the thing that we found. Well, actually, have you heard of dual quaternions?
No.
So, if you're just looking at rotations, which is the base level, then when you make this geometric algebra and you create even grade elements, what you discover is that they're actually the same thing, i.e. they're algebraically isomorphic. They have all the same multiplication rules. Then if you then create something called a dual quaternion, so you create this new thing, then you discover that you can do translations. And then what we've also discovered is, actually what we're talking about here are the dual quaternions. So although we've cast it in the language of geometric algebra, it's actually equivalent to using dual quaternions. But we like to use geometric algebra because this allows us to do things like prove results on derivatives. So this is why we've got geometric algebra.
I thought there might be a connection because you sort of hinted at it when you said that using complex numbers to do rotation, and then that sort of opens the door there.
Exactly, and perhaps from that picture you may be able to guess what IJK are.
Yes, of course.
Okay, further question?
So, how it is in terms of computationally, if you have to translate these geometric algebraic relations
Compared to matrices?
matrix?
Well, I was thinking about this the other day. They're supposed to be faster, so if you run quaternions on the chipset, so all the graphic designers have moved from rotation matrices to quaternions because it's supposed to be quicker. However, I haven't convinced myself that's necessarily the case. However, it's only going to be a linear order thing. So in other words, if I do a rotation matrix, it's going to take me 16 multiplications, whereas if I do a quaternion, it might take 32. But it's only ever going to be double. So there's not much scope in worrying too much about the advantages if it's not creating additional complexity.
One remark in our work on geometry, we have also switched to quaternion representation because when you need to invert things sometimes, the rotational matrices fail because they have singular points.
Yeah.
Quaternions help you to avoid that. So this is, I think, a higher value than just the computational efficiency.
I'll touch on that point if you want, maybe because you're quite interesting. So yes, when you have the quaternions, they behave sort of like a field, so you can always have the inverse, and there's a lot of stability issues. But if you decide that you want to port away from quaternions to dual quaternions, and then you want to define an inverse, then at the minute there are issues with this particular formation, but the one that Glenn Molyneux, I don't know if you, Professor Molyneux normally attends these conferences, we've just developed a new algebra that can solve that problem. So yeah, if you do decide to look at dual quaternions and you don't think that the inverse is stable, there may be one in the future.
Okay.
Okay.
Questions? I have one more question for you,
go on.
because I thought now that the next logical step in this work would be that once you have defined a curve including orientation,
Yeah.
then you could have a second description of actually the pose of a robot, yeah, and then you could set them equal, because then you know what the pose is at every instant of the curve, at least the pose and the orientation of the end effector. And I am wondering, because I saw in these equations that at least in the additive formulation, I saw a difference.
Yeah.
Yeah. So if you have two equations and you then rearrange them, you get in the denominator a difference which might be a singularity then, or at least an opportunity to have a pole. Have you thought about that?
We can, you talk about mechanical singularities.
Because you know that they are going to exist because your robot could move like this or he could move like that.
Yeah, so perhaps not necessarily in the entirely same flavour, but what work we have done is we've created this thing called retrievability of services, and we take a similar idea, we take a point and then an orientation of a point, map that into effectively what a machine would do, and then identify when we get occurrences of singularities. So in order to do that, you have to have some sort of analysis on the motion as you go through, and you're correct. If you think about additive and multiplicity, then maybe one version will be different from the other.
It was just a theoretical question motivated from the structure of the equations. Yeah? Not necessarily every artifact of the behavior of the equations will reflect the meaningful physical behavior.
Yeah, okay. A point on that, which I decided not to talk about, was the fact that when you're having a look at the additive case, you get things that are solved pretty easily. The multiplicative case is really hard because, as I said, these things anti-commute, which means they're not commutative, so I can't write expressions down. So that's one of the main reasons why this other expression works.
So, maybe the floor is open for further questions to all the presentations. So if maybe we start with the first one about the mesh segmentation with SB bijective transformations. Are there any questions still in mind about that presentation? Yeah, maybe people are suffering from exhaust. Okay, for the second about predicting haptic perception, other questions? Yes?
If I remember correctly, your order was that you first showed a detailed picture of a small area of the fabric and then of the whole product.
Yes.
And did you consider changing this order? Because I think in an online shop, most people would first look at a picture of the whole product and then maybe some detailed pictures. Because you said that there may be a correlance between the order.
Yeah, so there is correlation between the order, but we basically wanted to avoid that, mainly to see the effect of the high resolution images.
Okay.
So if they see the full image, then they already made the perception that.
Okay.
So that's why definitely it has that influence.
So the online shops have to change their images, so they see this.
They don't have to change, but for us to establish that there is an effect, we need to follow them.
Okay. Thanks.
It is such a pity that you cannot get a patent on the change of sequence. Okay. Yes?
I have a third question.
Yeah.
I was just wondering, I was not sure I understood why the connection between the first part when you analyze, you ask people to analyze image and make a connection to rough or not rough, and the haptic systems. What were the relation between the two types of projects?
Sorry.
Do you use the first, why do you need, the first part was about seeing if people could assess the roughness of textile by image, and then you have the, you spoke about haptic,
Yes.
and what was the relation between the two?
The relation is basically to create a system where we can experience experience, of course, there's no direct relation as such with the experiment, but mainly to see the similar effect, how it will happen in with a device like haptic devices.
Okay, so you just
Yeah, extending the same logic in a virtual environment.
Yes?
Perhaps just following on from that question, what I was wondering is why you chose people to give you your metrics, because obviously there's a lot of subjectivity
Yes.
from one person to another. I mean, I know why you did it, but I was just interested to know, could you have done it purely mechanically? So for things like surface roughness, we have more exact processes for doing it, and at least then you have something which is perhaps more consistent across a range of materials. Was there a reason for doing that?
If you do it purely on a mechanical basis, there are many other parameters which still need to be explored in terms of the textile manufacturing itself, like the number of threads, number of yarns, the type of weaving pattern. So all these parameters will get into the perception of, like, if you use double weft and single weft, then the perception of the smoothness and roughness varies. So not only the mechanical properties but also the manufacturing properties of the textile products also we need to consider, which becomes a slightly, the number of variables to be controlled is slightly higher, but we choose to do this more of a psychophysical analysis from human perceptive senses, mainly to evaluate at a perceptual level, not at a more of a technical level of that.
This
So,
also,
but still, we are still following this approach where we can purely based, like even if I know the material properties of one thread, so will I be able to figure out the haptic properties of that?
I mean, the key, which I thought was potentially really interesting, is around the stiffness, because for footwear, there are cases where you do definitely want something that's more supple, and then other areas of the shoe where you want to be much more rigid.
Yes,
So as you were sort of scanning over your contour,
yes,
that contour was really reflective of the geometry of the shoe.
yes.
Then there is actually, I think, quite a important use for that.
Yeah.
But obviously I appreciate it's very difficult to do that, because I think you had a box and people were blindly
Yes.
making a judgment call on that.
Yes.
I also have a remark to the scales of the metrics you use, because in psychological experiment people find out that human measurements are very often logarithmic and non-linear, because, for example, if we evaluate the weight of a letter with 20 grams, we can distinguish 20 grams plus minus 2 grams. Yeah. Meanwhile, when we weight a larger box, for example, which weighs 20 kilograms, we can no longer distinguish plus minus 2 grams. We can only say 2 or more or less kilograms. So it's very interesting that a lot of our human sensory information, due to the biological processing of our pre-processing of our cells, is logarithmic by nature. So this is Fechner's law, which is, of course, was German. So, any further questions? Yes, please.
I was just thinking, so if you want to use, so I was thinking in food industry sensory analysis, what you've done with people, if you want to improve your haptic systems, so in food industry, I will do that with professionals, but exactly can have kind of a reference and know exactly how to get the same result. So when they eat different food, they can exactly assess the palatability and the different properties. So I think if you want to use physiological results from sensory results for the haptic systems, it seems that it should be better with experts that can give you always the same result. And when they test, the haptic system tells you, yes, this is the same roughness than the real, I feel the same roughness than the real tissue, textile. So maybe, also if it's something you want to do, maybe it's the way to do, I'm not sure.
Yeah, so the approach which we are taking is to, like what he suggested is purely from a mechanical properties perspective. You identify the parameters and then through the device you simulate the haptic textures. But in terms of perception, it still varies either whether you do it in a real environment or you do it in a virtual environment. So that variation is still is there.
Okay, I think we can move on. If there are no further questions to this presentation, we can move on to remaining questions of the non-manifold modeling of lattice structures. Yes?
Well, this is just a very general question. My observation of computers over the decades is that the processing power becomes so much more powerful that people perhaps are less interested in the internal efficiencies, which is more the top-end performance. So my just general question is, what was the inspiration for this when computing power is increasing, doubling, quadrupling?
Okay. Particularly, computational power is increasing, but not really, for us. For us in particular, we didn't have the computational capacity to be able to simulate a large domain, and we cannot update at the speed that the technology also develops. So, we needed a low-cost solution for a problem that we had, and we needed it to be more efficient. And that's why it inspired us.
Maybe one remark. I think that I could not really see exactly in the domain what the real benefit was, but I think that with upcoming rapid prototyping techniques, we will have amorphic structures, and we know that with conventional modeling methods, I know from a huge airframe manufacturer that they wanted to have a 10 centimeter long bar. They modeled in CATIA V5 using little spheres for the amorphic material, and they used up the whole 32 gigabyte memory, with a 10 centimeter long bar. So this clearly indicates that for new materials where we have structures at the meso or even at the micro scale, we need new modeling techniques, and therefore, even though it might be difficult to understand, more mathematics always helps.
So, comments and a pseudo question, because I think I know the answer, but it ties into what both of you have said. So as a computer scientist, I definitely think we can't rely on Moore's law to deliver, indefinitely. We're sort of reaching the end of Moore's observation rather than law. And so any advantages we can get, we should definitely take them. And then particularly not everything's been scaling kind of at the same rate. Memory is certainly something that's lagged behind it. So it all seems to offer improvements on both, computational and memory usage sides. So I think that that's definitely worthwhile. And then my pseudo question is, it didn't look very parallelizable. It's not, right?
I don't
That's a
know.
whole other research question.
I cannot answer that question right now. I don't know.
So it's off the top of my
I
head.
would have to evaluate it, but I don't really know.
For the resources, I can also add a pseudo remark. When I did my bachelor's thesis, I used an Apple II computer with 32 kilobytes of RAM, and it contained an operating system plus an application program of the complexity of Excel, which at the time was called Lotus 123, plus user data. Today, only if you have a Windows screen, the icon you see when you click on something might have 32 kilobytes of memory. So this is wasting resources is one which doesn't really help, especially when we can always scale problems up. In 72, a crash model for a car was 6,400 elements. And today we talk about 6 million. And you can imagine in 20 years how many more elements we will have. Okay, great. Types of freeform motion. Any nasty further mathematical questions? No, everybody is happy that we already passed our math exams. Yeah, so this basically brings me to an end. I think we did a good job in surviving the last section of the conference presentations. I was glad to be your host, and I can even give you the certificates of attendance. So while going out, please make sure that you grab your certificate, and if yours is not there, maybe it's in another section, so make sure that you don't go home without your written certificate. Thanks for coming.